Alright, so now we can take all of these different terms that we've defined and we can write down our vorticity transport equation. So this will just be time rate of change of vorticity plus u dot del omega is going to be equal to omega dot del u plus, so those are our two terms from advection, plus our del rho cross del p divided by rho squared plus the diffusion of vorticity so each of these terms, right, we have local time rate of change of vorticity here we have basically the advection. Right, if you look, this looks just like our advection term, so this is our advection of vorticity. This term on the other side that we've put over here, this is our vortex stretching. And reorientation term. From our pressure term, we have what we refer to as the baroclinic torque term. And then we have our last term is our viscosity term, or our viscous diffusion of vorticity. So now what we can do is we can go through and kind of talk a little bit more about each of these different terms. So first is basically what we have on our left-hand side, and this is really just the material derivative of, so our first component of the vorticity, right? So we can simply write that time rate of change of vorticity plus the advection of vorticity is simply, by definition, material derivative of vorticity. So what does this tell us? This just gives us how fast the vorticity changes along a fluid particle trajectory. Right, so just how that's changing. Next term we can talk about, so that gives us those two terms. We'll save the stretching term till later. Next we can talk about, we have the baroclinic torque. So what is baroclinic torque? This was this term over here on this side of it. And this term results in a generation of vorticity because of as a result of the density and pressure gradients not being aligned with each other. So this generates vorticity as a result of misalignment between del rho and the gradient of our density and our pressure gradient. So obviously this term is only important, or only plays a role at all, if rho isn't constant everywhere. Which we already saw that there are cases like this where we can have incompressible flow that also has a density gradient. Right? These are our density stratified fluids. So that's where this would play a role, is if you have a density stratified fluid. So let's look at a example, or just kind of how this works out. So let's consider following thought example. So basically, when we have the gradient in the density is perpendicular the gradient in the pressure when that happens. So what we're talking about is we have basically high density here, we have low density here. So this is our kind of representation of gradient in rho. So rho is basically we're getting more dense as we go up. And then say in the other direction, we have a pressure gradient that goes from low pressure to a high pressure region. Right between the two of them, where we basically have kind of a coordinate system looks something like this, where we'll call this y, we'll call this x. So we have pressure increasing as we go from right to left, and we have density increasing as we go up. Now, if we think about this, basically our pressure is related to our force, right? Or in the end, if we think about Newton's second law, the acceleration of a fluid particle is just going to be equal to force over the mass, right? So what does this mean? It means that low density fluid will accelerate faster for a given pressure gradient. Right, is what this actually means. In the above example, all the fluid, right, the pressure gradient is only in the x direction, right? So all the fluid sees the same pressure gradient. So all fluid which is basically our force, right? They all see the same pressure gradient, or they all see the same force. Since the lower density fluid down here will have a smaller mass, it'll accelerate faster than higher density fluid. Right? This basically will generate a shear flow and cause a net circulation in the clockwise direction. Right, so we have fluid moving faster here than it is here due to the pressure gradient. So basically, and the reason why we say clockwise, well, because we basically have that, in this case, the gradient in our density only acts in the j direction, and the gradient in our pressure just acts in the I direction. So that if we look at this, the cross product between the two is just going to be minus omega k. Or basically we're going to generate vorticity directed into the page from this. Our next term that we'll talk about is our viscous diffusion. Alright, so this is basically the process by which non-vortical fluid gets vorticity as a result of a basic redistribution of the existing vorticity due to molecular interactions and the exchange of linear momentum between fluid particles. So this is just by which non-vortical fluid gains vorticity as a result of existing vorticity due to molecular interactions and the exchange of momentum.